Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 49, and it is entitled Motion in a Vertical Circle and Electric Power. These are two topics that are completely unrelated, and we'll take them one at a time. Let's begin with motion in a vertical circle. I have a clip of a program I would like to play for you, and I think it speaks for itself.
Welcome back. Right, I'm really excited about this next item because it's the biggest and bestest thing fifth gear has ever done.
Hell yeah, check this out. Who remembers these? Hot Wheels and Loop the Loop. Come on, Tom, send one down.
There we go.
Yes, but what we wanted to know is could you do that in a real-life family-sized car?
Yeah, we gave the job to our friendly neighbourhood stuntman, Steve Trulia, but we wanted some questions answering first. How fast would he have to go? Would the car stick to the road? And would he black out under the G-forces? Clearly, scaling a toy up to a record-breaking 40 feet high using 5 tons of steel and a real-life motor was going to be dangerous. So we sent Steve to Cambridge University's Dr. Hugh Hunt to find out how fast he'd have to go.
2r plus a half v in squared.
Starting to cook my brain a bit now.
36
About
miles
36
per hour.
miles an hour.
But you know what we haven't worked out though?
What's that?
Is what are the G-forces you're going to experience? Because you want to know whether you're going to black out or not. The total G-force you will experience as you enter this loop will be 6G.
It gives me a bit more confidence because of the science, but at the end of the day, I don't know if that's going to count when I'm staring at the track with my foot in the accelerator.
To lessen the chances of Steve blacking out at the wheel, he needed to get used to pulling 6G. The only place to do that was in this.
Here we go, into the loop! Oh my! Feel the G pulling! G! Pulling my face again! Oh!
Stunt Day. The day fifth gear finds out if you really can drive a car around a 40-foot high loop-the-loop. If successful, stuntman Steve Trulia will set a new world record. If he fails and falls out of the loop, the massive deceleration forces as he hits the ground could be fatal. 36 miles an hour had been calculated as the ideal entry speed. Slower than this, and he'd fall. Much faster, and the G-forces would knock him unconscious and exert a dangerous force on the ramp's structure.
Here we go, this is it. This is it, we're going in too fast. And here we go. Rock and roll! Wow, I did it! Oh, that is fantastic! It was so light at the top. I really thought I'd lost it. I felt weightless. I thought, I'm falling. I'm so glad that I stayed in touch with the road all the way around. As soon as I left the ramp, just a complete feeling of joy and elation.
Dr. Hugh Hunt's analysis revealed how close we'd come to disaster. Just 2.5 miles an hour slower, and Steve would have fallen.
And here we go.
1 mile an hour faster, and the extra friction caused by the scraping would have made him fall as well. Steve hit it spot on, so take a moment to savour the world record for driving a car around the largest loop-the-loop. Chances are you'll never see it executed so perfectly ever again.
Wow, I did it!
We've already talked about motion in a horizontal circle, and generally that has been uniform circular motion. One of the points that I'd like to make about vertical circular motion is that it is not uniform. And in general, it's going to have speeds that are slower at the top than at the bottom. When we say that circular motion is uniform, What we mean is that the speed of the object as it goes around the circular path is constant. Whether I'm swinging a bucket of water around and around overhead, whether I have someone riding on a roller coaster that makes a vertical loop, or someone who's riding on a Ferris wheel, whether there is someone in an airplane that's doing a loop-the-loop, or some other amusement park ride. If I have motion in a vertical circle, frequently there's going to be things that happen around the circle that are not going to be at constant speed. It may be that the speed will be constant, say like in the case of a Ferris wheel, but frequently the speed will not be constant. At this point, I'd like to show an animation that illustrates some vectors that occur during vertical circular motion. In this animation, there is a blue mass which is moving in a vertical circle, and there are a couple of vectors that are shown in this animation. The red vector illustrates the velocity, and the black vector that's along the radius of the circle shows the tension, say in a string, as the mass goes around and around. It speeds up at the bottom. Up at the top, if I have the object moving at the critical speed, then there is no tension needed in the string to keep the object in the circular path. I'm going to show one more vector here, which is the weight vector. So this is the force of gravity acting on the object as it moves in the circular path. That gravity vector, that weight vector, is constant throughout. But you can see that the direction that the radius vector makes with respect to the weight vector is constantly changing. And the velocity is changing as well. What we want to do in this lesson is to learn how to analyze such motion. Let's sketch a diagram and illustrate some of the things that we mean. Here's an object of mass m that's moving in a circular path of radius r, and it has a tangential speed that is v, and this object's moving in a vertical circle. We don't know in this general situation what forces there are acting on this object to cause it to go in a circular path. It may be that this is a stopper that's whirled on the end of a string, and if it is, then the force that's causing the centripetal motion is a tension. It could be that it's a car making a loop-the-loop, in which case it's the normal force that is holding the object in the circular path. It might be that this is a person sitting on a Ferris wheel, in which case it is gravity that's holding the person in the circular path, but there's also a normal force of the seat acting on the bottom of the person that accelerates them. It could be that this is a person making a loop-the-loop in an airplane or a roller coaster, in which case the seat exerts a normal force. We don't know what forces are acting until we have a specific problem, and each problem has to be looked at individually. The general strategy that you're going to use to solve these problems is to sketch a good free body diagram, to apply Newton's second law for circular motion, and to take the direction of the centripetal acceleration as the positive direction. Those three steps are probably going to be the same for each type of problem that you get. So the forces that are involved may be different from problem to problem, but the way that you approach these problems is first to sketch a good free body diagram showing all the forces, apply Newton's second law, taking the direction of the centripetal acceleration to be the positive direction. More than 90% of the problems that you're going to face are going to be problems in which you're asked to look at two strategic points of the motion. That's going to be at the very top of the circle and at the very bottom of the circle. One more quick point before we begin to take a look at some specific examples, and that point is that there will be a speed that is called the critical velocity that the object has at the very top of the circle, in which the only force that's acting on the object at that point is the object's weight. What other radial forces are at work on the object disappear at the very top, and only the object's weight holds the object in the circular path. In this video of this car making the loop-the-loop that we saw at the beginning of this lesson, there is a calculation of how fast the car has to be going at the very top of the loop in order to get around without falling down. And so this magical speed that the person had to enter the loop with was based on that speed at the top. Now, how fast he entered the loop and how fast he was going at the top were two different speeds, but that critical velocity at the top was calculated, and then the entrance speed to that ramp was adjusted based on that critical velocity. Let's take a look at a specific numerical example. John attaches a string 1 meter long to a 2 kilogram ball and swings it in a vertical circle so that its speed at the top of the circle is 18 meters per second and the speed at the bottom of the circle is 25 meters per second. A. Determine the tension in the string at the top of the circle. B. Determine the tension in the string at the bottom of the circle. And C. Determine the critical velocity for this system. Here's a diagram of the motion. I'm taking a snapshot of the motion of the object when it's at the top, when it's moving at 18 meters per second, and at the bottom when it's moving at 25 meters per second. The object has a mass of 2 kilograms and a radius of 1 meter in this vertical circle. Let's begin with part A, figuring out what's happening at the top of the circle. Let's sketch a free body diagram of the object at the top of the circle. What forces act? Well, there are two forces. One of them is the object's weight, which acts straight down. The other is the tension in the string. And when the object is at the top, the tension in the string acts along the radius, which is also straight downward. When I'm at the top, the direction of the acceleration is toward the center of the circle, which in this case is downward. So when I'm at the top, I'm going to call the downward direction positive because that's the direction that's towards the center of the circle. So now let's write Newton's second law for this situation. Newton's second law says the acceleration is equal to the net force divided by the mass. In this case, the acceleration is centripetal, so it's going to be v squared over r, where v is how fast the object is going, in this case at the top of the circle, and r is the radius of the path. The net force is equal to the forces in the positive direction minus the forces in the negative direction. Both of these forces are in the positive direction, so the net force is going to be the weight plus the string tension. Now what are we trying to find? In part A, we're trying to find the string tension at the top of the circle. Well, I claim that I know all these numbers except the string tension. So I want to solve Newton's second law for the string tension, put in the numbers, and come up with a numerical value for the string tension. So I'm going to solve this equation for Ft. If you'll permit me, I'll do it in a single step. The weight is a number I can calculate since I know the mass. The weight is equal to m times g. Let me put all these numbers in and let's figure out numerically what the tension is when it's at the top. Now let me substitute the numbers into my calculator. I find that at the top, the string tension is 628 newtons. Let's go on to part B. Let's find the string tension at the bottom. Again, let's sketch a free body diagram. But let's realize that at the bottom, the string tension acts towards the center of the circle, and the weight is still going to act towards the ground. Now, what's going to be the positive direction in this case? The positive direction I choose to be the direction of the centripetal acceleration. When the object is at the bottom, the center of the circle is in the upward direction, and so I'm going to call up positive at this particular position. Now I'm ready to write Newton's second law. Newton's second law says the acceleration of the object is equal to the net force divided by the mass. The acceleration is centripetal, so it's v squared over r. What about the net force? Well, it's going to be the positive forces minus the negative forces. The only positive force I have right now is the string tension, Ft. The weight now is in the negative direction, and so I'm going to say that the net force is the string tension minus the weight. Now what are we looking for? Again, we're trying to find the tension of the string at the bottom of the circle. If you'll permit me, I'll solve for the string tension in one step. Now you'll notice that Newton's second law looks similar to what it did in the top situation, but there is a sign difference, and that has to do with the direction of the acceleration and the direction of the forces. And now we substitute in the numbers, put those numbers into the calculator. Notice that I'm using the speed of the object at the bottom now because that's what situation I'm looking at. That speed is different than it was at the top. I get that the string tension down at the bottom is 1270 newtons.